So this is some joint work with two people. Rajiv Datta, who's a student at CMI. He should be on the job market very soon. And his mentor, advisor, Partho Mukhopadhyay, also at CMI. Okay. So let me start very slowly and just interrupt me whenever something is not clear. And anyway, this is my first foray into arithmetic complexity, so I am also learning as we go along. So you may please point me out some errors that I'm sure going to make you. So the two central questions that we are sort of the defining questions. One is, of course, the famous P versus NP question from Boolean complexity raised by Cook back in 1971. And then we will also look at the algebraic analog of it called VP versus VNP, V for Valiant, and therefore was raised by Valiant in 1978. In both questions, there has been total lack of progress. But in the case of Boolean complexity, the object that we study are Boolean functions. Okay, and in the case of algebraic complexity, the objects that we study are formal polynomials. So formal polynomials over some favorite field of yours. So in this talk, mostly, almost always, my field will be the field of real numbers. Okay, so these are formal polynomials, and because here you have to compute formal polynomials, you may expect there's a lot more structure that you can make use of. For instance, I mean, you should certainly be able to make use of the deep tools in algebra that has been developed over years to make progress. And so it seems that this question, the question about separating VP from VNP, by the way, are you able to see my mouse? I intended to use it as a pointer.
Yeah, we can see it.
Okay, great. So, all right. So the algebraic complexity question should be easier, and it seems should be more tractable. And the Boolean complexity question is perhaps more difficult. In fact, you can make it formal as well. So you can show if the field is well behaved that a separation between P and NP necessarily must separate VP from VNP. So there's some formal reasons as well, but let's not go there. So as I said, there's however, we have perhaps made more progress with algebraic complexity, but it's surprising that we haven't made as much progress as one hoped we would have made because of the things that I said. So one success that has been true for both the models is what is called the monotone model, and what is going to be our main focus today. In the case of algebraic complexity, the monotone model might be slightly tricky to define. So the way we'll define is the following. So a polynomial, which is what we want to compute, would be monotone if all the coefficients in its monomials are non-negative. Okay, so I'm over the real numbers as I said at the beginning. So then such a polynomial would be monotone. And of course, there is a monotone circuit to compute a monotone polynomial. A monotone circuit is one which does not use any negation or negative sign or any cancellation. Okay. So
Arkadev, you didn't even say what a circuit is, but basically you are allowing addition and multiplication to compute, to compute polynomials, and you don't allow addition with negative coefficients.
Right. Okay. Thanks, sir. Yeah. So a circuit is a natural thing that you would imagine to compute polynomials. You have these variables, and you have addition and multiplication gates, and you can use small constants in the wires connecting gates to other gates. And if you have a monotone circuit, then you cannot have the -1 as a constant in your wire. Okay, so that's what I mean by a monotone circuit, and it's not difficult to see that every monotone polynomial does have a monotone circuit. The question that we are interested in is in the complexity of that. What is the smallest size of a monotone circuit computing a monotone polynomial? So, some examples of polynomials that we will encounter is polynomials that come out of matrices, like the permanent of an n by n matrix. So that's a polynomial on n square variable. So this matrix is filled with formal variables. It's a symbolic matrix, and we look at its permanent. So it has n square. It's an n square variable polynomial with degree n. And we will only look at polynomials whose degree is a polynomial function in the number of its variables. Okay, so the permanent is an example of such a monotone polynomial. Another example, the famous counterpart, is the determinant. And the determinant is not a monotone polynomial because it has negative coefficients as well. So in the monotone model, we, as I said, so the permanent is just like the SAT is to in Boolean complexity. Permanent is considered the cardinal example of a polynomial which is not in VP. So if one polynomial one would bet would separate VP from VNP, most people would bet it to be the permanent. Okay, in fact, the permanent is VNP complete. So what early on, this work of Shamir and Sneer from 1979 showed is that the permanent polynomial cannot be computed in polynomial size with monotone computation, with monotone circuits. So this is the class that we will call MVPM for monotone.
Arkadev?
Yes.
Yeah, maybe it's good to say that the permanent polynomial has exponentially many monomials. So the obvious way to compute it would just to compute each monomial with its coefficient, which would be +1, and this will be exponential size. So the question is whether you can save, and that result says you cannot. In fact, it's an exponential lower bound.
Right, it's an exponential lower bound. Yes, as Avi said, that it has exponentially many monomials. So if you were to compute monomial by monomial, you can compute it in depth too. You just have one sum gate, and then you have product gates feeding into it. But the fanning of this sum gate would be exponential, as many as the number of monomials. And this lower bound of Shamir and Sneer is saying that essentially, you can do some savings. So there are some savings that can be done from this circuit using something called the Riser's formula, but I don't want to go there. But this lower bound says that basically there is not much of cost saving that you can do. By the way, the circuit that I said, the depth 2 circuit, is a monotone circuit for computing the permanent.
Okay, I have a quick question for you. So monotone real circuits, are they stronger than monotone algebraic? And I know the objects are different, but
come again, monotone real, are they stronger
so
than
monotone, like monotone real circuits where they're for functions, not for polynomials, but the gates can compute any monotone function of the inputs. So
but so you have gates that are computing functions, but how do you compare them exactly? Because
maybe it's too specialized. Maybe you want to, because it's
maybe
really,
okay.
Really a different object that.
Yeah, but I know you're going to use communication complexity, so that's what brings the question to my head. But it's okay. I can.
Yeah. So should we take it later?
Sure.
Okay. So, right. So as I was saying, so this argument that Shamir and Sneer used is actually a very simple combinatorial argument to show that that permanent is not monotone VP. And the counterpart of this thing in the Boolean world took a much longer time, and it was this sort of breakthrough work of Razborov from 1985, when he showed that the monotone function click, again, a Boolean function is monotone if you make it's monotone if the value of the function only changes from 0 to 1 if you make certain input variables go from 0 to 1. Okay. So if the function outputs 1 at a particular input, then it cannot output 0 by changing a certain variable of that input from 1 to 0. Okay, such a function is monotone. So when I'm talking about the computation of click, the input is a graph, and the inputs is a graph, and the edge variables are the variables that the circuit gets as input. So if you add an edge, if you had a click, the click would continue to remain. That's what makes the click function obviously monotone. And what Razborov showed in 1985 is that the click, which is also an NP-complete problem, is not in monotone P. Okay? And this argument, I think, is much more delicate than showing that permanent is not in monotone VP, which again reaffirms the intuition that results in Boolean complexities seem to be more difficult to obtain. So there has been many other successes with the monotone model. Okay, I don't want to get into all of them or list all of them. The kind of question that we are interested in this talk is to understand how much does negation or cancellation help in computing monotone functions, because after all, these functions are monotone, right? So you think perhaps that negation cannot help much when we want to compute a monotone function. So this question was answered first in the algebraic world again, and this was answered by Valiant in 1979, who showed the following polynomial. So now again, you take any graph, planar graph, and look at the matching polynomial. The matching polynomial is a monotone polynomial, all of whose monomials, each monomial of it, so it's a multilinear polynomial. Every variable occurs exactly once, at most once in a monomial, and the edges that monomial selects, it's the matching polynomial, because if the edges in the monomial, the edges that are selected in a monomial, if they form a matching, a perfect matching of your graph, then the coefficient of that monomial would be 1. Otherwise, the coefficient is 0. Okay. So given a graph, you can talk about this matching polynomial. And what we know using an algebraic trick called the Pfaffian, that if you take a planar graph and look at its matching polynomial, then it does have polysize circuits. So therefore, it is in VP. And what Valiant showed is that for a certain family of planar graphs, the corresponding matching polynomials cannot be computed cheaply with monotone circuits. So thereby, he showed that even to compute a monotone polynomial like the matching polynomial, cancellations can help you exponentially. His lower bound was exponential, so that gave you an exponential separation of the power of cancellation. Again, the answer for the Boolean complexity had to wait 6 or 7 years. I might get these dates a little bit wrong. And Razborov showed that now the matching function, so in the Boolean case, the matching function is, again, you're given a graph and you want to find, let's say, even a bipartite graph, and you want to find out whether this bipartite graph contains a perfect matching. This, of course, we learned in our basic algorithm course that this has a polynomial time algorithm. Surprisingly, what Razborov showed was that this does not have polynomial size monotone circuits. Now, the separation that Razborov was able to obtain here was barely super polynomial. It was quasi-polynomial separation, whereas the separation due to Valiant was exponential. Okay, so now we have exponential separations between, even in the Boolean world, between the power of negation and the power and monotone computation. But for matching, this remains an outstanding problem. Whether matching has a sub-exponential size monotone circuit is still not known. So then you may ask, so what's there more to know? Okay, so in the same spirit, we would like to ask this question in this talk, which is the following. It's a very natural question. We want to understand what is the simplest model of general computation that allows for negation and cancellation, which is exponentially more powerful than the most powerful monotone model, the unrestricted monotone model. Okay, that's the question that we want to understand. Again, this question makes sense both in the Boolean world and in the arithmetic world. In the Boolean world, as Razborov showed, that matching which is in P is not in monotone P. In fact, matching turns out to be in randomized. So it has a very fast randomized parallel algorithm. For complexity theorists, it's in randomized NC. In a similar vein, Raz and Avi showed that matching cannot be computed by sub-exponential size monotone formula. So this is again showing a separation, an exponential separation of powers of models with cancellation and models without cancellation. And very recently, there was a paper by Gus and Mika Gus and others from 2019, which showed some function which can be computed deterministically in very fast parallel time for complexity theorists in NC2, whose monotone complexity, circuit complexity is exponential. Okay. So that's the story that we know so far in the Boolean world. Analogously, in the algebraic world, it turned out that there was not much progress on these lines. So Valiant's result, as we just saw, is still there. Soon after Valiant's result, there was another result by Jerem and Sneer, who also showed similar result like Valiant, but for a different polynomial, a very important polynomial called the spanning tree polynomial. Okay, so that's the story so far. And now what we'd like to understand is sort of ask the most extreme form of this question. So the question is, can there be constant depth circuits, general circuits, which allows for cancellation and negation, that can exponentially beat unrestricted monotone circuits? Okay, so this is, if one could prove such thing, this would be the strongest possible qualitative separation between the powers of negation and monotone computation. Okay. In Boolean complexity, this is open. In algebraic complexity, this was open until our work. However, in the non-commutative model, so when I have talked about algebraic complexity, and in this talk, we will only focus on the commutative model, but there is a non-commutative model where you can think of the variables to be like matrices, matrix value, and so they do not necessarily commute. And things are a little easier there to prove. We know more in that model. So in that model, for example, this question was has a strong positive answer due to the work of Rubish and Yehudayev from 2013. Okay. And in this work, our main result, one of our main results is to show a similar result as the result of Rubish and Yehudayev, but for the more common commutative mode. So I'll take a pause here and ask if there are any questions. Please feel free to stop me if something is not clear. Okay, so everything seems to be clear. Let's move on. So informally, this is the theorem that we are going to prove, that there exists some polynomial with capital N variables. Okay, and this polynomial is going to turn out to be a very special kind, like a set multilinear polynomial. I'll come to it later. The degree of the polynomial is going to be quite reasonable, square root of n, if you ignore the log factor, such that this polynomial can be computed by a depth 3 formula of reasonably small size, just above quadratic, under cubic. But the monotone complexity is going to be exponential. Okay, 2 to the n to the 1/4. Okay, in the exponent, I'm ignoring log factors. Now notice this is sort of optimal in the following sense. Yeah? So if I allow only depth 2 circuits, okay, then there is no difference in the power of monotone computation and non-monotone as far as computing monotone polynomials is concerned, right? Because this remark is just saying that every function that can be, every monotone function that has a poly-size depth 2 circuit with cancellation will also have a monotone poly-size depth 2 circuit. Okay, this is an interesting exercise if you want to try it out, but this is not, I mean, it's reasonably straightforward. Okay. So in that sense, this separation is qualitatively optimal. So we cannot have any power of negation or cancellation in depth 2, but here we show that in depth 3, you already have significant power.
So maybe since you didn't formally define it, so depth 2 is just the sum of products. So this is really representing the polynomial more or less in the usual form, and that sort of at least a little bit explains the remark. And depth 3 would be sum of product of linear forms as opposed to variables, right? Products of linear forms. And that's already, you say, is expressive enough to get an exponential separation.
Right. Depth 2 could also be a product of sums, but anyway. Yeah.
You cannot do much with it.
You cannot do much there, right? Okay. So in the rest of the talk, I will focus on this. So the main part of the talk is I'll try to give you an intuition as to how do you find this polynomial P. Okay, that's how we started the project. At that point, it was not clear at all whether, I mean, we didn't think that communication complexity would enter so explicitly. And it turns out that even to find this polynomial P, intuition from communication complexity at least guided us in a very serious way. Okay. And then the next question is, how do we prove? Once we have found a P, how do we prove the monotone lower bound that we need for P? And here the connection to communication complexity is, I would say, more obvious because, if you look at all previous papers on monotone arithmetic circuits, they all draw their intuition one way or the other from communication complexity, perhaps not explicitly, but certainly implicitly. Okay, almost all papers, not maybe every paper. Okay, so and what we will see is to find this polynomial P, we will make use of a particular famous conjecture in communication complexity called the log-rank conjecture. And to prove our lower bound, we will use a new connection to communication complexity, and this connection will be very, very explicit. And this connection also is sort of, we find interesting in its own right, because what it led us is to do another thing, which is a first step for general lower bounds. When I say general lower bounds, I mean lower bounds for not necessarily monotone circuits. As suggested by Pavel Rubish in a very recent and I would say surprising paper. But since I have only so much time to talk, I won't talk about this latter result. I will only focus on this theorem that I just stated. Okay, but you can ask me offline. I'll be very happy to explain. Okay, so how do we find out this polynomial? So we're looking for some powers of cancellation, and the polynomial with which we have most success using cancellation is this determinant polynomial. There have been lots of algorithms for the determinant, and all of these, of course, use very non-trivial cancellations. I mean, for those who know, this is called non-multilinear cancellation, but never mind. If you don't know, it's not. It's just that some very powerful cancellations take place here. Okay, and these cancellations. So again, for those who know, this would be these can be done in arithmetic branching programs. But it doesn't matter. It's if you don't know, it's like in VPs, and it can also be done in VNC2. But it seems that it's mostly believed that these kind of cancellations, it's very hard to push them down in constant depth. It would be shocking if the determinant had efficient circuits of constant depth. Okay, so we cannot look there. Then the other cancellation that is also quite surprising is Benor's trick, which uses interpolation. Okay, and again, Avi might correct me because I couldn't find a reference. I mean, I've heard it from so many people. So the only place that I found reference to is in Avi and Amir Shpilka's paper from 2001. So I just put down 2001. So I don't know.
He never wrote it down. It's it's probably from the late 90s, and he just never wrote it down.
Okay. So this is interpolation, and this uses multilinear cancellations again for. So the interesting thing is that these kind of cancellations are carried out in depth 3. So depth 3 circuits already have interesting power. In particular, they can compute, the elementary symmetric polynomials. okay, which is a monotone polynomial. So you may hope that therefore perhaps one can try using the elementary symmetric polynomials to prove our theorem. Unfortunately, I don't want to go into details of it, but unfortunately there's a very simple way to compute efficiently by monotone circuits elementary symmetric polynomials. So this kind of power that interpolation gives us seems to be also not sufficient for our purposes. So we would like to therefore find out.
Hi. Just a comment. For formulas, it does give you a separation. For monotone formulas, you cannot compute the symmetric polynomials in polynomial size.
It's in the same paper you mentioned of Snir and Shamir. They prove an n to the log and lower bound for symmetric polynomials for formulas.
That's right. Yeah. Well, it is a, so it's not an, okay, that's true, but it's not an exponential separation, and we are also looking at monotone circuits.
Yeah.
Okay, but thanks. Yeah, thanks for the remark. So now we are looking at some. Oh, by the way, hi Amit. I didn't see you. You were there. Okay, so so we are looking for some new way of cancellation, and in depth 2 circuits. So you know what other way to look at than random depth 3 circuits? Okay, I mean, if random depth 3 circuits do not cancel, then what else will cancel, right? So let's look at random depth 3 circuits, and let's make it even simpler. So these are set multilinear circuits, okay, which means that I have let's say n blocks of variables, and each block has m variables. So naturally, I'm going to use 2 indices to index into this n times m variables, okay? And let's look at a depth 2 circuit, which is now actually a pi sigma circuit. Okay, so the top gate is an n-fold product gate, and the bottom gates are the sum gates. And these B1 to Bm, these are some constants, actually will be 1 or -1, which I will choose at random. Okay, so I just choose them at random from 1 to -1. And the same B1 to Bm, notice that the same B1 to Bm are being used in each one of these sum circuit. Okay, so one for each block. This is block 1, block 2, block n. Okay, let's understand. So that's the depth 3 circuit. Let's understand what's going on here. Right. So now, given such a depth 2 circuit, I mean, you just make a depth 3 circuit by summing up various such depth 2 circuits. And for each depth 2 circuit, you choose its own copy of these constants. So first I showed you one depth 2 circuit. It had m random variables in 1 -1. And now I'm having capital N many such depth 2 circuits, and I'm summing them up. And each of the depth 2 circuits gets its own array or vector of random variables from 1 -1. Right? So this is 1 -1 to be. Is this clear? And now I would like to understand what the pattern of cancellation. Now notice that this every monomial that we have here, every set.
So maybe you're about to answer this. So the only thing they're doing is the B's are just permuting the variables. So I'm not sure I understand the B1 through Bm.
No. So these B1s are just some multipliers. So they have either value 1 or -1.
Wait, so what's
either
the random is sorry. Okay, gotcha.
Right. So either you're feeding it or you're feeding its negation.
I see. Sorry, I misunderstood completely.
Good, thanks. Okay, so so now we would like to understand what happens to what is the coefficient of a monomial in this circuit. Now, a set multilinear monomial of this type, yeah. So it takes exactly one variable from each block, and it takes one variable from each block, and there are n blocks. So basically, a monomial of this kind, you can naturally associate with it a map from n to m, right? I mean, it tells you from the ith block which variable it picked up. So yeah, so we can interchange this language. Every monomial comes with a map, and every map associates with a monomial. So the coefficient of such a monomial is exactly this, right? So and so if you look at the ith subcircuit, the coefficient of the contribution towards the coefficient of a monomial kappa from the ith subcircuit would be the product of the b's from the ith block according to their permutations, right? You just multiply sigma 1, sigma 2, and so on up to sigma. This is the contribution of the coefficient of the ith subcircuit to the coefficient of kappa. And then you want to see what happens. You just rearrange it in the following way. So you go through all possible of these indices. There are m indices, and pretend for a moment that the mod 2 is not there. So bi of L, well, it will be raised. How many times does it appear in this product? It appears there as many times as L was hit by the map sigma. Right? So it's the cardinality of the pre-image of L according to sigma. But then I said that each of these are 1 minus 1 value. So it's just a parity, it's mod 2. Right? So it's this whole product is either 1 or minus 1. That depends on the parity of the cardinality of the pre-image of L. Okay. So this is the contribution to a coefficient by the ith subcircuit. And if we now go back to our depth 3 circuit, if you look at the coefficient of kappa, so I just add up the contributions from each of the subcircuits. Now, what you see is all that matters to understand is what I call the parity vector of kappa. So what is the parity vector? The parity vector is you look at the pre-images of the map associated with kappa for each one of these m possible elements in the range, and look at their parities, the cardinalities, the parities of the cardinality. That gives you an m bit vector. Okay, and that is what I call the parity vector of the monomial kappa. So it's easy to see if the parity vector was the all zero vector, that means the monomial kappa was such that the map sigma associated with it hit everything in the range an even number of times, right? Then the coefficient of that kappa would be exactly 1, right? Because each of the subcircuit would contribute 1, yeah, and there are n things, and I've normalized it by 1 by n, so the whole thing would be 1. There would be no cancellation. This is the monomial that never, there is no cancellation happening with this monomial. Okay, but for every other monomial, yeah, whose parity vector is not the all zero vector, it will cancel. If I chose my b's at random, then in expectation you would see 0. Okay, so the observation is that the parity vector determines the coefficient completely, and it determines in exactly the way that I just said, right? So if the parity vector is the all zero vector, then the coefficient of kappa is 1. Otherwise, you expect it to be 0 if you chose it random. Okay, in expectation. Well, you can choose, instead of these random things, you can choose a pseudo-random object like an epsilon biased space. So B1 to Bn can come from some suitable pseudo-random representative. And for a concrete example, I'm taking an epsilon biased space because it's efficient. So I can choose just a few of these. How many? How few? Well, order m by epsilon square. And then when I choose it in that way, again, the all even vector would be 0, but every other monomial would cancel heavily. In particular, its coefficient would be at most epsilon. Is this clear?
Maybe it would be, well, I don't know, maybe for some people it would be useful to think about first where the BIs were all possible vectors, just and then basically you would get you'll get exponentially many, and then you will get perfect cancellation except for the right monomials, and this would really be Reiser's formula for the permanent if m equals n. So you are sort of de-randomizing the Reiser formula using epsilon biased vectors.
That's a nice way of
Yeah, because there you have inclusion, exclusion, and everything cancels perfectly. And here you, okay.
Yes, yes. So if I was allowed to use exponentially many depth 2 subcircuits, then I would go through all possible BIs, and then I would have perfect cancellation, as Avi said, and it would be 0. But I can't afford to do that because I have only polynomial size. So I'm choosing a suitable representative of that, which is an epsilon bias space, and one possible representative, and then it will still cancel heavily all the monomials except the all 0 monomial. The monomial whose parity vector is all 0. Okay, so the question is, how do we exploit this? So this is the kind of cancellation that's happening, and we would like to exploit these things to create our function. So before we do that, now let's say that this gives us a sort of a nice way to generate from Boolean functions some polynomials. I call them 0, 1 polynomials because in these polynomials every coefficient is either 0 or 1. Okay, so take some function, Boolean function f, from m variables to 0, 1. And now I define a polynomial p of f in the following way. Well, first of all, I want to make it set multilinear. So the coefficient of a monomial kappa is 0 if kappa is not set multilinear. And if it is set multilinear, then I just evaluate f on the parity vector of kappa. Okay, so this gives me a nice way to, a natural way to associate a polynomial with every Boolean function in. Okay, and these are set multilinear polynomials with 0, 1 coefficients. And what do we need from f? So remember, I want p of f. My ultimate aim is to show that there is some f such that p of f is easy for depth 3 circuits. Okay, and at the same time, I want to show that p of f needs exponential size unrestricted monotone circuits. These are, of course, opposing goals. At one point, in one way you want to make it easy, the other way you want to make it hard.
You also want it to be monotone.
Yes, you want also to be monotone. So far, well, I mean, the way I said they are monotone, right? So p to the f, because f is 0, 1 valued, so they would be monotone.
But it seemed like you would get epsilon in some coefficients. The epsilon can be negative.
That's right. Well, that was when I was showing you how to compute them. But the way I've defined p of f, you will always get monotone, right? Because f is a Boolean function 0, 1, right?
Yeah. Here. Yeah. Okay.
Yeah. We'll come to that, and we'll deal with it. There is a very easy way to deal with what I was pointing. But now let's try to understand. So here's how we are getting into connection with communication complexity. Let's understand this goal of the polynomial being easy for depth 3. Okay, let's understand it from the rank perspective. Okay, so suppose you have f such that p of f is easy, so it has this set multilinear depth 3 circuit. Okay, so now look at some partition of your blocks into 2 sets A and B. Okay, it's an arbitrary partition, and with respect to this partition, there's a natural object matrix to look at, where the rows are indexed by all set multilinear monomials which depend on the variables from the blocks in A, and the columns are all monomials which are set multilinear and depend on the variables from B. And an entry corresponding to the row MA and MB, where MA and MB are some monomials, set multilinear monomials, is just the coefficient of the polynomial P of f of this monomial MA times MB. Okay, this is a very natural matrix to look at, and what we see immediately is that the rank of P of f, sorry, the rank of this matrix with respect to this partition A of B is at most S, where S is the fan-in of the sum gate, right? Because if you think about it, the depth 2 circuit it's a product gate, right? So the product gate, if you think about it, it's a rank 1. It's giving you just the decomposition that you need, the rank decomposition, because each product gate contributes rank 1, and you're just summing S many of them. Okay, so this is the whole rank is at most S. So this all in all just means rewording it that, well, if it is a set multilinear circuit computation of depth 3, then P of f must have low rank. Okay. Okay, all right, but we still have the hardness condition. Now let's try to understand the hardness condition. The easiness condition has now translated into low rank with respect to all partitions. So the way lower bounds are proven in arithmetic world is via this what are called structure theorems. So what does a structure theorem say? It says the following. It just says, suppose I have a polynomial P that has monotone complexity S at most, then it can be decomposed into a simpler it can be decomposed as a sum of simpler polynomials, where each simple polynomial is a product polynomial. So here the product polynomials are alpha I, beta I, so there are S plus 1 of these things. And interestingly notice that each of these, for each I, alpha I is a set multilinear polynomial that depends on variables from the blocks in IA, and beta I depends on variables from blocks in IB, and together IA and IB, they form a partition of the blocks. Okay, and they form somewhat of a balanced partition. None of these is too large. So this is the decomposition. And
maybe it's good to give a reference to Hiafil. I mean, it's a major basic technique that goes back to Hiafil from the late 70s.
Okay, so I didn't know of that. Okay, so this was okay. So Abhi is pointing out the correct reference. Yeah, as I said, I mean my knowledge about arithmetic circuits is quite sketchy. So I'm yeah. Thanks, Abhi. So the interesting thing, the important thing here to notice is the following: is that each I. For each I, you have a partition induced on the blocks, but these partitions can be very different from one another. This is the subtlety about this decomposition. Okay, so IA, IB need not be the same as JA, JB for I different from I different from J. But with respect to a particular I, okay, with respect, I mean for the partition which is corresponding to this I, it's again a rank 1 decomposition. A product polynomial is always a rank 1 with respect to this specific partition. The whole thing is not saying that the rank is at most S or S plus 1. And one important thing I forgot to mention is that alpha I and beta I, of course, monotone. So this is a monotone decomposition. Okay, so there's no cancellation going on. So this says that the non-negative rank of alpha I bi with respect to this fixed partition is exactly 1. And as I said, most lower bounds would go through for monotone circuits would go through the following way. It would prove, in order to prove the monotone lower bound, it would just show that such a decomposition, such a small decomposition, is not possible for your target polynomial using some techniques. Okay, this is the idea that they use. So if you want to use that idea, then what does this imply? It immediately implies that for every balanced partition, okay, AB of the blocks of variables, with respect to that partition, the non-negative rank of your polynomial must be at least S. Okay, so if we put back these two conditions, so we saw two two rank conditions that came out of one out of the easiness condition and one out of the hardness condition. The easiness condition said that with every partition, the rank, ordinary rank, is at most, it's small, it's at most R. The hardness condition says, on the other hand, for every partition, the non-negative rank is large. Okay. I mean, it's saying something more, but it's at least, this is a necessary but not sufficient condition to prove your lower bound, right? Okay. So you need you need to come up with a polynomial where these two things are satisfied at the very least, yeah, to achieve your objective. And this turns out already to hit a barrier in communication complexity, the log rank conjecture. Because if you were able to come up with such a polynomial with 0, 1 coefficients, okay, then you would immediately get a refutation of the log rank conjecture. And we don't know of such a refutation. Okay, so what is the log rank conjecture? Let me just tell you at this point, what is the log rank conjecture? It's a very nice and tantalizing conjecture, which says the following. I'm just referring to its matrix theoretic form, stripping it of its communication aspects. Okay, so in the matrix theoretic form, what it says is the following: for every Boolean matrix, there exists some universal constant alpha, sorry, says that for every Boolean matrix M, right, the log of its non-negative rank is at most a polynomial of the log of its ordinary rank. Namely, the polynomial, the exponent of the polynomial is this universal constant alpha. Okay, this is the essence of the log rank conjecture. So, and this is, this is exactly in opposition with what we wanted. Okay, so therefore, this avenue is blocked until and unless we are able to disprove the log rank conjecture. In fact, if the log rank conjecture is true, this will never give us the kind of separation that we wanted. So this is still wide open. So we want to avoid the log rank conjecture. We already see that the log rank conjecture comes in here. And the way we will avoid is sort of to go to another conjecture, which was, so we can't deal with 0, 1 polynomials which have 0, 1 coefficients, because then the log rank conjecture comes in. So we want to deal with polynomials that are almost, that have almost 0, 1 coefficients, not quite 0, 1. And there is a version of the log rank conjecture for that, that is relevant here, which is called the log approximate rank conjecture, which was made much later in its formal, in a formal way by Lee and Scheibman from 2007. Again, in the matrix theoretic form is the following: for every constant epsilon, there exists some universal constant alpha, such that if M is no longer a Boolean matrix, but it's an approximate Boolean matrix. Right? Each of its entries is very close to either 0 or 1. Then the log of the non-negative rank of such an M is at most a polynomial in the log of its ordinary rank. Okay.
For those it's not obvious, this is a much stronger conjecture than the previous one.
It's a much stronger conjecture than the previous conjecture. That's right. So it implies in particular the previous conjecture. Okay. But it's an interesting conjecture because it depends on how you prove if you want to prove the previous conjecture and you use techniques that do not use the Booleanness of M, the techniques go through for a slight perturbation of M, then it would also prove the log approximate rank conjecture. Okay. So it's a much stronger conjecture, and therefore it's probably, already the log rank conjecture seems too good to be true, and this seems even worse. And that what turned out to be true. So we were recently able to show, along with Nikhil Mande and Suhail Sharif, that this conjecture is actually false. Okay, and and because this conjecture is false, now this gives us a hope in our investigations on the arithmetic front, because now we can hope to use the counterexample that we have in this that we showed for this conjecture to look at functions which are not, to look at polynomials which are not exact, whose coefficients are not exactly 0, 1 valued, but they're close to being 0, 1. Okay, and I'll tell you more clearly what I mean by that. So let's look at the counterexample to this log approximate rank conjecture, because this is going to be the key function that we are going to use to our for building our polynomial. So this is a very simple function called the sinc function. And to understand the sinc function, you think of it in the following way, which is you have a complete graph on k vertices, and the edges of this graph, there are k choose 2 edges of this graph. These are the variables, okay? And the sinc function does when you look at an assignment to your input variables to the edges, they orient the edges in a certain way. So if you give value 0 to an edge, then let's say for convention, the edge orients from the vertex which has a higher number than to the vertex which has a lower number. Doesn't matter, but this is the convention I'm following. And if you assign 1, the edges orient the other way. Okay, so this is the orientation, and now this becomes a tournament once you orient the edges. And the question is, as the name suggests, the output of the function is 1 if and only if there is a sinc. Now, the interesting thing about this function, very, very simple, is that if there is a sinc, there is exactly one sinc. Either there is no sinc or there is exactly one sinc. So there's some sort of a promise, even though the function has no, I mean, all inputs are kosher, the function has a promise. What I mean by that is that this particular feature of the function can be used very nicely algebraically. It seems like an innocent thing, which is the following, that you can write the sinc function exactly as a sum, where each summand checks whether the vertex vi is a sinc or not, because there is at most one sinc. So you can sum them up. Okay, and this was exploited to disprove the log approximate rank conjecture, and this is also going to be used to build our function in the way that we want. And so it turns out that sinc will help us improve the theorem of Valiant. So let me just define one more definition. So I say a function, given a function f, Boolean function, g is g approximates the Boolean function well if g and f pointwise are close. G is not Boolean, but at each point it evaluates close to what f evaluated. Okay, within epsilon. And then our main theorem is the following. There exists some g which is not a Boolean function, but it's a very good approximant to the negation of sinc. It's a bit of a technicality, to the negation of sinc, such that the polynomial p to the g, remember, given any such function g, I was able to extract a polynomial p to the g. This polynomial will turn out to have polysize depth 3 arithmetic formulas. There will be some such g. However, for every g that is a delta approximant to non-sinc, the monotone complexity of p to the g will be exponentially large. Okay, and if you just put these two things together, you see that whatever we wanted is immediately follows. Okay, so how much time do I have, Avi? I mean, I'm happy to go on.
Yeah, I said 5 minutes unless you want to bargain.
Okay, so if it's 5 minutes, then okay, so that's yeah. So maybe I should just explain why sinc is in depth 3, because that's the easiest thing to explain. Okay, and I will have no time to tell you how do you prove the lower bound.
Maybe somebody will ask you.
Yeah. Okay, and then we can go back. We can go back to it. All right. So let me just tell you how why sinc is in depth 3. Okay. So this is exactly just we saw a few slides back why the definition of sinc can be expressed as a sum of these indicator functions, right? And let me give you an example. So let's say, you know, k is 5 and m therefore is 10, the number of edges. Okay. So we want to compute. So I'm going to give you a depth 3 circuit to check if the vertex V3 is a sinc. If I can give you depth 3 circuits for each such vertex, then of course, if you sum them up, you still get a depth 3 circuit. because the top gates are sum, so you collapse, and you will get a depth 3 circuit for all of sync, for the whole sync function, right? So in order to check if V3 is a sync, notice what you have to do is to look at the inputs to sync and see if it lies in a particular sub-Q, right? Because in order for V3 to be sync, all you need to do is to check whether these these edges are oriented in the right way, right? Every edge incident on V3 should be oriented into V3, which means some of the edges should receive 0, some of the edges should receive 1. So that's a sub-Q. You check if a particular sub-Q is there. Now, in the context of depth 3, this means, a particular monomial, a particular monomial, you look at the parity vector of that monomial, right? So the parity vector of that monomial is an assignment to the edges of sync. I hope I have not lost everybody, right? So I'm in this depth 3 circuit, which is computing p to the sync, let's say, right? So there, if it is computing p to the sync, in a set multilinear monomial of p to the sync, this you want to basically look at the parity vector of this monomial, right? And then the parity vector gives an assignment to these variables, the sync variable, the edge variables, and then you want to see whether that assignment makes V3 a sync, right? Okay, so how do I do this? So I need to show you how to do that. Because if I can show you that, then as I said, I can sum up over all the vertices, and that will give me the whole thing to sync. So here's the trick. So you want to check whether this is in the subcube, and notice I'm going to exploit, recall we saw the pattern of cancellations that happen in this depth 3 circuits, right? I'm going to exploit that cancellation. So these things in purple, 0, 0, so the purple says that these variables have to be set to 0, right? So and the things in gold, this golden yellow, these means these things have to be set to 1. And the stars are, I don't care what they are. Those edges can orient in whatever way they want, right? Now, what I'm going to do is the following. So now M is the number of, remember in the set multilinear case, M is the number of variables in each block. But now M is being represented as the number of, corresponds to the edges of a complete graph. So I'm going to naturally refer to each of these M variables inside a block by a pair of indices, from the graph. Now, okay, so for all these stars, I don't care. So there's no B attached to this star. So these are coefficients 1. So I'm taking a product of linear forms, and in each of these linear forms, which corresponds to, this is an n-fold product corresponding to each of these blocks. And for the variables which are stars, I don't care. I always have the coefficient 1. So if you look at this polynomial, what I claim what this polynomial does is the following. You look at its coefficients that this polynomial spits out. If the set multilinear you look at the monomials that this polynomial spits out, look at the coefficient of a set multilinear monomial. I claim that if the parity vector of that set multilinear monomial that you are looking at, if in its 1, 3 position, so again, the parity vector is an m bit long vector, but now m is being indexed by a pair of variables. So if in its 1, 3 position, if the parity vector has a 0, right? Then there is so the coefficient of this monomial would not be would be 1 exactly if in the 1, 3 position the parity vector is a 0, in the 2, 3 position the parity vector is a 0, In the 3, 4 position, the parity vector is a 1 because I've sort of negated it by post multiplying, flipped it by post multiplying it with another copy of B34. Okay. This is just a matter of verifying, but this is what happens. Okay. So, and on the other places, it doesn't care because there it always has a 1. Okay. So this is exactly saying that if the parity vector lies in the subcube 0, 0, 1, 1, then there would be no cancellation. If the parity vector does not lie in the subcube 0, 0, 1, 1, then because my B1 to BR are chosen carefully from an epsilon bias space, which is like a, you know, sort of random points, there would be heavy cancellation. So in other words, this polynomial PV3 will have those monomials whose parity vectors lie in the subcube to be 1, and those which do not, their coefficients will be very small. This is the crux of the thing. And now I just sum them up. Okay, one corresponding to each VI. Okay, and the polynomial Q that you get, it will have only those monomials will have large coefficients where the parity vector corresponds to an assignment of, where the parity vector corresponds to a sink, and those which do not correspond to a sink, they will have very negligibly small coefficients. They can be negative. Okay, at this point they can be negative. And you can make it, as Avi said, how do you make it monotone? There's a very simple way to make it monotone. You just look at the non-sink polynomial. This is why the non-sink comes in, and you subtract it from the full polynomial here. The corresponding algebraic operation is to subtract it from the full set multilinear polynomial. If you subtract it, then everything will be positive. This is easy to check because this polynomial Q, either it had coefficients 1 or very close to 0. So if you subtract it, it cannot become negative because all the monomials in the full polynomial had coefficient 1. Okay, so this makes it a monotone, an honest to God monotone polynomial. Okay, which is now closely approximating the non-sink polynomial. And this is the polynomial that we show has monotone complexity large, but I think I'm way out of time. Sorry for getting into this. So let me just skip the perhaps the most interesting technical part of the talk, which is how do you now prove a lower bound for this object? Okay, which is where all these interesting ideas from communication complexity would come in. And let me just end with the open problems. So one obvious open problem is to improve the bound. That is, what we showed is that we showed a polynomial which can be computed in constant depth, but which requires monotone complexity exponential, but not strongly exponential. Okay, so a natural question is, can you find a polynomial even in constant depth, not depth 3, maybe depth 5, depth 6, whatever, large depth, but constant, but whose monotone complexity is still strongly exponential? Okay, that would be very nice. We don't know any such thing. The other thing would be to, can you prove it's the Boolean analog of this? So can you prove the analogous theorem in the Boolean way? Can you find a monotone Boolean function that can be computed in constant depth AC0, right? Constant depth, but which requires exponential monotone circuit. In fact, even exponential monotone formula size, we don't know. Yeah, even exponential monotone formula size, we don't know. Okay, which should be approachable from a communication complexity style of argument. And finally, I didn't have the time to show you the lower bound techniques. There's some optimism to believe, you can ask me offline, that these techniques might extend to just more general models, not just monotone models, at least to the set multilinear, which is already as powerful as a non-commutative model. So if you can prove lower bounds on the set multilinear model, that would already imply general non-commutative lower bounds. So it would be very good. And even better if you can prove it in the multilinear model. Okay. And I'm optimistic that communication complexity theoretic techniques would be useful here. Okay, thanks for your attention.
Okay.
Sorry to be way over time.
It was great. So let's open the floor to questions.
Seems like it was completely clear.
Okay, you want to say 2 sentences about the lower bound, or however many you want to.
Yeah. So okay. So right. So let me just open up this slide that I couldn't show. So I want to open up the slide which shows the main differences between communication complexity and monotone arithmetic complexity. So the major difference. Okay. So, both Avi and Amir they are experts, so they can correct me. My point of view is the following. So the similarity comes from the fact that the structure theorem in the arithmetic world says that if the polynomial has small size circuits, then it decomposes into a sum of product polynomials. And individually, each product polynomial is a rank 1 thing with respect to its own partition. So it does seem to behave like a rectangle. Not quite a rectangle, but like a rectangle. So it seems to say that, well, okay, you want to show that a certain function cannot be, decomposed as a sum of a few rectangular things. Okay, that's what makes you believe that communication complexity methods should have a say. Okay, but there's an important difference here, which I think is a major difference, which is why I think we are stuck with even sec multilinear lower bound, is that in the communication world, yes, you do prove that something cannot be decomposed into a sum of few rectangles, right? But each of these rectangles has a fixed partition. They are rank 1 things in a very nice sense, right, with respect to the same partition. Whereas when you decompose into product polynomials, each product polynomial has its own partition. So you need to use an argument that's able to work against these varying partitions, unlike in communication complexity. Okay. So, standard communication complexity does not deal with this varying partition. There is communication complexity with varying partitions. There is a term for it, I forget, but it's still different.
I think it's called any partition.
Okay, any partition, right. So any partition.
Very clever name.
So, but any partition is also a little different in the following sense, because from what I understand, in any partition, you have one function and you say, well, however you partition it, the communication complexity is still large. But when you're proving a lower bound on the communication complexity, you stick to that partition. In the arithmetic model, it's a hodgepodge, right? I mean, you're sort of summing up and you're using in each of its product polynomial a possibly adversarially chosen different partition. This is still seems to be different from any partition lower bounds. And this, I think, is the major difference. Okay, once we know how to handle that, we will be able to prove lower bounds. The way we handle this in this particular paper is that we observed if we build our functions in this way, the way that I showed you with a Boolean function f, this gives you a certain way to handle this, because these are set multilinear polynomials, right? So what's happening is this corresponds to an XOR function, f of XOR, right? Because you give a balanced partition. Each of this product polynomial has a balanced partition of the set of blocks. And if you think about it, then it seems like no matter whichever partition you do, it boils down to computing f of XOR under the standard partition, where Alice gets a bunch of an m-bit vector and Bob gets an m-bit vector, and they have to XOR their m bits and compute f on that. Because we are building the function in this way, I mean, you have to argue this. It's not completely obvious. You have to argue this because you have to prove a certain equidistribution. It's very simple, but you have to carefully argue this, that there are, I mean, these things are sort of equidistributed, and so if this is balanced partition, you are always sort of, even though the partitions themselves are different, you always reduce. A product polynomial with this varying partition will be a rectangle in the fixed partition communication model. Okay, this is the trick that happens. Okay.
So
and
it just it was for any polynomial defined in the way that you did, that you know, p to the power g, this type of
yes.
You really, I mean, essentially have to deal at the end with a fixed partition as opposed to
yes. This is the simple intuition, and in order to make it formal, you have to do a bit of work. Yeah, I mean, in particular, what we do is basically we say that whenever you prove a corruption bound on f of XOR functions, it lifts to a corruption-like measure for polynomials. So we define a corruption-like measure for polynomials, and then we say there's a one-to-one correspondence, like a transfer theorem. Whenever you prove, no matter how you prove your corruption bound, if it is proved under a certain kind of distribution, there's a bit of an annoying thing. It has to be a certain kind of distribution, but most distributions are of that kind. Okay, when you prove a corruption bound of that for distributions of that kind, then it corresponds to a high corruption bound on with respect to product polynomials. And once you get that kind of corruption bound, then you can prove your monotone lower bound.
Great. All right, more questions.
Yes, I have a question. Thanks, Arkadev, for the very nice talk. So if can you hear me?
Yes. Hi, Igor.
So hi. So if you only wanted to give a separation, but not a tight depth-3 formula upper bound, is that a simpler argument, or you essentially get it for free using these techniques?
Yeah, so that's a good question. So you're saying, suppose you don't want it depth 3, you can use larger depth, right? So we thought about it. I mean, you know, we couldn't. I mean, the point is, it's like a double-edged sword, right? I mean, so if you sort of use more powerful circuits, then you start wondering what kind of cancellations can you exploit there, right? I mean, you have more power, but you know, you just sit back and marvel at it, and nothing comes out. At least nothing came out when we tried. But
I see. Thank you.
Maybe there is a way.
More questions. All right, Arkadev, this was great. Thanks a lot.
Thank you very much.
Thanks. It was great.